Welcome to Math's Zone African Motives. In this tutorial, we'll be diving into a fundamental concept in calculus. Our main goal today is to prove that the derivative of the cosine function is negative sine. This proof is a classic example of using the first principles definition of the derivative, which helps us understand where the differentiation rules come from. By the end of this video, you will be able to follow and reproduce this proof step by step. Before we begin, please take a moment to read the full question on your screen. This is what we will be proving today. We'll be using a method that relies on two important tools: the first principles definition of the derivative and a trigonometric identity. Understanding these is key to unlocking the proof. By using this method, we can build a strong logical argument to show the relationship between the cosine function and its derivative. Our proof begins with the definition of the derivative, which is often called the first principles definition. The derivative of a function f at x, written as f prime of x or dy dx, is defined as the limit as h approaches 0 of f of x plus h minus f of x, all divided by h. This formula might look complex, but it simply calculates the slope of the line tangent to the curve f is x at any point x. We do this by finding the slope of a second line between x and x plus h, and then letting the 2 points get infinitely close together, so that h becomes 0. Now let's apply this definition to our specific function. F of x equals cos of x. First, we identify our function. F of x equals cosine of x. The first part of the definition is f of x plus h. If f of x is cos of x, then f of x plus h must be cos of x plus h. We're essentially just replacing the x in our original function with x plus h. This gives us the two parts we need for the numerator of our limit. Now we can substitute these expressions into our first principles formula. So, the derivative of y with respect to x is the limit as h approaches 0 of the cosine of x plus h minus the cosine of x, all divided by h. We've now set up the core expression for the proof. The next challenge is to simplify the term inside the limit so we can evaluate it as h approaches 0. To simplify this expression, we'll need a key trigonometric identity known as the compound angle identity for cosine. The identity states that the cosine of the sum of two angles, alpha and beta, is equal to the cosine of alpha times the cosine of beta, minus the sine of alpha times the sine of beta. This identity allows us to break down the cosine of a sum of angles into products of sines and cosines of the individual angles. It's a fundamental tool in trigonometry that will apply directly to our expression. Let's apply the compound angle identity to the cosine of x plus h. In our case, alpha is x and beta is h, so cos of x plus h becomes cos x cos h minus sin x sin h. We've now successfully expanded the term that was causing our limit to be difficult. This expansion is a crucial step in the simplification process. Now, let's substitute this expanded form back into our limit expression. The limit now becomes the limit as h approaches 0 of cos x cos h minus sin x sin h, and then we subtract the original cos x, all divided by h. We're making good progress. The next step is to rearrange and factor the terms in the numerator to reveal some familiar limits. The next step is to rearrange the terms in the numerator to group the cosine terms together and then factor out a common factor of cos x. So we group cos x cos h and minus cos x together. From these two terms, we can factor out cos x, leaving us with cos x times the quantity cos h minus 1. This factorization is key because it separates our expression into two distinct parts that we can handle individually using standard limits. Now that we have factored the numerator, we can separate the limit of the sum into the sum of the limits. This gives us two separate limits. The limit as h approaches 0 of cos x times cos h minus 1 over h, and minus the limit as h approaches 0 of sin x times sin h over h. Because cos x and sin x do not depend on h, we can factor them out of their respective limits. This leaves us with two standard limits we need to evaluate. This simplifies our expression to cos x times the limit of cos h minus 1 over h, minus sin x times the limit of sin h over h. We have arrived at two standard trigonometric limits that are essential for completing this proof. While proving them from scratch is a separate, more involved process, they are results you will encounter frequently in calculus. The first is the limit as h approaches 0 of the quantity sin h over h, which equals 1. The second is the limit as h approaches 0 of the quantity cos h minus 1 over h, which equals 0. You can think of these as fundamental building blocks that we can now use to evaluate our main expression. We will substitute these values directly into our equation. We are now at the final step of our proof. All that's left is to substitute the values of these standard limits into our simplified expression. Our expression is coes, x times the limit of cos h minus 1 over h, minus sin, x times the limit of sin h over h. Substituting the values we just learned, the first limit becomes 0 and the second becomes 1. So we have cos x times 0 minus sin x times 1. This simplifies to 0 minus sine of x, which equals negative sine of x. And there we have it. We have successfully proven that the derivative of y equals cos x is dx equals sin x. Let's quickly recap what we've accomplished. We used the definition of the derivative, also known as the method of first principles, to find the derivative of the cosine function. First, we applied the first principles formula. Then we used the compound angle identity to expand cos of x plus h. Next, we used algebra to rearrange and factor the terms. Finally, we substituted the values of two standard trigonometric limits to reach our final answer, negative sine of x. This step-by-step process demonstrates how a seemingly complex calculus problem can be solved by combining basic algebraic, trigonometric, and limit principles. This process is how the fundamental rules of differentiation are established. Thank you for watching this tutorial from Math Zone African Motives. We hope this step-by-step breakdown has made the proof of the cosine derivative much clearer. Subscribe for more tutorials from Math Zone African Motives. See you next time.